Okay, so in this video, we now want to look at, having looked at in the previous video, approximating the area under a curve. We now want to look at how we can find an exact area under a curve. Okay. Now there is some algebra between those two steps that shows how we get from approximating the area to the exact area. But it's a bit beyond the scope of what we're going to cover this year. However, I am just going to, before we get to this, to detour it across to give you the idea of what actually happens in that process and how we end up using our definite integrals to find exact areas. This will be very loose and it's not in any way a proof and it's not in any way justifying the algebra of it for you, but I just want to give you a sense of how we go from those approximations to those exact areas. Okay, so here we have a function. It's a simple sort of parabola by the looks of it. Yeah, in fact the rule's down here at the bottom right, so yes, it's an upside down parabola. And we're approximating the area between x equals 0 and x equals 10 under this curve. And at the moment we're approximating it using the right endpoint estimate with 5 intervals of equal width. And we see that that approximate area is an underestimate, it's 560. The program is also calculating the actual area for you, which is actually 666 2/3 square units. So if we were to look at what happens is, obviously if we wanted to improve our approximation, the key thing that we can do is to increase the number of intervals. Okay, so the more intervals we use, obviously the narrower each of the rectangles are, and hence the closer and closer and closer we are able to get to the exact area. So in fact the algebra of what happens in the background, which we won't be looking at, is again to do with taking a limit like it is for derivative. So we calculate the approximate area and then we look at taking the limit as the number of rectangles approaches infinity, or as the width of each rectangle approaches 0. That's actually the key. So we look at as we increase the number of divisions, the width of each rectangle gets closer and closer and closer to 0, and the actual area approaches the approximate area approaches the actual area. And so essentially again it's a problem about limits. Okay, and we look at, as I said, as we use lots and lots of rectangles, the approximate area gets closer and closer to the actual area. And if we look at the limiting value, we can calculate the actual area. And that's where we lead to the definite integral. The definite integral gives us the exact area. Although there are some caveats to that, not every definite integral corresponds directly to an area. We have to think quite carefully about what's happening, and we'll have a look at that today. Okay, so finding the exact area under the graph. So as we previously established, a definite integral is an integral calculated between two limits. So if we calculate the integral of f of x from a to b, we do that by finding the antiderivative of f of x, which is capital F of x, and we substitute b into that, and then we subtract and substitute a. So we've looked at already the algebra of how we evaluate the definite integral. Today what we want to do is connect that to area. As I said, not every definite integral has to be about area. Not every definite integral directly corresponds to an area, but they are used in calculating areas. So if f of x sits on or above the x-axis between a and b, so that is that f of x is greater than or equal to 0 over the interval from a to b, then the definite integral gives the area of the region that is bounded by the x-axis and the lines x equals a, x equals b, and y equals f of x. Okay, so this integral here gives this area here. The integral from a to b of f of x. It gives that area there. Okay, as long as f of x is on or above the x-axis. Alright, so we'll come back to what happens if it isn't on or above the x-axis in a minute. So let's use calculus to find the area of the shaded region. Okay, so this is an area under a curve. It's the area under the curve y equals x squared. So it's going to be x squared we're going to need to anti-differentiate. So the area is going to be the antiderivative or the integral of x squared. And we want to find an area between x equals 0 and x equals 2. Okay, so we're going to integrate from 0 to 2, and that integral will give us the area between that curve, x equals that value, x equals that value, and the x-axis. Okay, and we can already see from the diagram that between x equals 0 and x equals 2, the function is on or above the x-axis, and so therefore the integral corresponds directly to the area. Alright, so let's evaluate this then. So antiderivative of x squared is x cubed on 3 from 0 to 2. And And so then that is 2 cubed on 3 minus 0 cubed on 3, so that's just 0. So it's 2 cubed on 3, which is 8 on 3. Now it's an area, and so it is in square units. Now again, not every definite integral should you be writing square units after that, but if you are calculating an area, that is in square units. If it's a problem with context and you've been told all measurements are in meters, then it would be in square meters or kilometers, whatever it might be. Okay, so the integral from a to b of f of x represents an area if the function is on or above the x-axis. So what happens if the function goes below the x-axis? So let's have a look at this. Let's use area formulas to work out this area, and then let's see what happens when we calculate an integral. So formula for the area of a trapezium. So remember, it's area equals half times a plus b times h, and again remember that's where a and b are the parallel side lengths, and h is the perpendicular height. So in this case, h is this distance, and a and b are the vertical distances. So this, we're going to need to work out these points, the coordinates of these points, so we can work out the vertical distances. So the rule is x plus 1. So when x equals negative 2, y will be negative 2 plus 1, so that's negative 1. So that means that distance there is 1. Okay. When x equals negative 4, y will be negative 4 plus 1, which is negative 3. So that means that that distance there is 3. Okay. That distance there is 2. Okay. And so therefore the area, using the formula for a trapezium, is half times a plus b, which in this case is 1 plus 3, times the height, which is 2. Half times 2 is just 1, so it's just 1 plus 3, which is 4. 4 square units. Okay, so let's then have a look at, alright, we know the function's under the x-axis, and therefore we know that the integral doesn't directly give the area. So let's see what the integral does give, though, given that we know the area is 4 square units. So if we integrate from negative 4 to negative 2, so always from the smaller to the bigger value, this function, okay, even though this function is below the x-axis here, let's work out what that gives us and see if we can have a look at what's happening. So antiderivative of x plus 1 is x squared on 2 plus x, and we're doing that between negative 4 and negative 2. So we sub in negative 2 first of all, so we're going to get negative 2 all squared, which is positive 4 on 2, minus 2. Take away negative 4 all squared, which is positive 16 on 2, take away 4. Alright, so that is 2 minus 2, so that's 0. Take away, that is 8 minus 4, which is 4. So it's going to be negative 4. Okay, so the definite integral gave us negative 4, and the actual area was 4. Obviously, you can't have a negative area. You can't say this integral does not equal the area. Area cannot equal negative 4. So you need to be careful about just writing, when you write down area equals something, be really careful that you're not saying that area is negative. So the area doesn't equal this integral. The area equals the negative integral. So the area is actually equal to the negative of the integral from negative 4 to negative 2 of x plus 1 dx. You might remember from our properties of integrals that if we have a negative, what we could instead do, instead of sticking a negative out the front, we could instead switch around the limits of integration. Okay, and that's the same thing. And obviously this is just one example, so it's in no ways a proof, but this is actually true. So for regions below the x-axis, the area is given by the negative integral from a to b of f of x. Or we can write that as the integral from b to a of f of x, so we can switch the limits of integration instead. So what's really important is that you have to actually look at the region that you're trying to calculate the area for. You have to draw the graph and see whether the region is above or below the x-axis, or potentially whether it crosses over the x-axis, in which case you're going to need separate integrals. So let's have a look at some examples here. So for the function y equals 3x squared minus 12, use calculus to find, part A, the definite integral from 0 to 3. So this is not asking you to make any consideration whatsoever about area. You're just finding the definite integral from 0 to 3 of 3x squared minus 12 with respect to x. Don't forget your dx's. Antiderivative of 3x squared is 3x cubed on 3, so that's just x cubed. Antiderivative of 12 is 12x. We're going to sub in 0 and 3. So 3 cubed is 27, minus 12 times 3, which is 36. Take away, that'll be 0 minus 0. Again, please don't ignore the step of consciously thinking about substituting 0 in, because otherwise you will struggle next year when subbing in 0 doesn't give you 0. Alright, so 27 minus 36, so that is negative 9. Okay, we don't need to make that positive to make it an area. The question is not asking about area. The question is asking you to evaluate a definite integral from 0 to 3. And we've done that. It is negative 9. A definite integral can equal a negative number. An area can't be negative, though. So part B, we want to now calculate the area bounded by the curve, the x-axis, the lines x equals 0 and x equals 3. Okay, so we've got the diagram drawn for us. If it hadn't been drawn, we would have needed to draw it ourselves. Now what we notice here is that actually, if we want to calculate the area bounded by the curve, the x-axis, the lines x equals 0 and x equals 3. So if we draw those things in, so curve is that line, the x-axis is that line, x equals 0 is that line, and x equals 3 is that line. So we're looking for the regions that are bounded by those lines. Okay, and that's these two regions here. So bounded have to be completely enclosed by those lines. Alright, so we're going to need to calculate this area, but what we see is that a bit of this area is below the x-axis, which means we need to use a negative integral, or we need to switch the limits of integration, and a bit of this area is above the x-axis, so we don't need a negative integral for that bit. So that means if we want to find area here, we actually need to split this as two separate integrals. So in this case, the area is going to be equal to the negative integral from 0 to 2 of our function, which is 3x squared minus 12, plus the positive integral from 2 to 3. And you have no choice but to do that if your area crosses over. Now personally, I prefer, rather than have negatives hanging around, it's easy to lose them, I prefer to substitute the limits in the other way around and write it this way. Okay. Antiderivative, we've already worked that out previously, so we know that's going to be x cubed minus 12x. We're doing that from 2 to 0, plus then we're doing x cubed minus 12x from 2 to 3. So lots of terms, just take your time, don't lose track of things. So we're first substituting in 0 and then taking away and subbing in 2. So 2 cubed is 8 minus 2 times 12, which is 24. And then we've got plus, we're subbing in 3, which is 27 minus 36. Take away, substituting in 2, which is 8 minus 24. And yes, we could put some brackets around here, but actually they don't make any difference because we're adding those things. If we were subtracting, we need to be a bit careful about that. Okay, so this is 0, take away, 8 minus 24 is negative 16, plus 27 minus 36 is negative 9, take away, negative 16. Alright, so what have we got there? Minus minus 16, so that is 16, take away 9, and then minus minus 16 again, plus 16. So 16 and 16 is 32, take away 9 is going to be 23 square units. And that obviously doesn't have any correlation to this definite integral of negative 9. Actually it does. If we were to work out, what we're finding here is that this is negative and this is positive, and if you're just doing the straight integral, they're essentially being added together all at once. So what you're finding actually is that amount of area is cancelling out that amount of area because it's positive and negative, and essentially the negative 9 is just corresponding to the bit that you've got left. So it's not actually connected to the area at all, and so therefore it's not just about calculating the integral from 0 to 3 and then making it positive. You have to think about the region that you're looking at, okay? And in this case we have to divide it into two separate integrals because it crosses over the x-axis. Okay, let's do a couple more examples. Calculate the area bounded by x squared plus 1, x equals negative 2, x equals 2, and the x-axis. Okay, so we need to draw a graph. Y equals x squared plus 1 is a parabola translated up by 1. Okay, so that's going to be 1 there. And then we want to find the area from negative 2 to positive 2. X equals negative 2 is a vertical line, x equals positive 2, sorry, it's negative 2, is a vertical line. And so we're trying to find the region bounded by the curve, the line x equals negative 2, the line x equals positive 2, and the x-axis. So this is the region we want to find here. The other thing you see when you draw the graph is that you notice any symmetry. Now I haven't drawn my diagram's not very symmetric, but we know that the parabola is symmetric, and so actually we know that what we could do is instead just find that area and double it. Okay, so if you can do that, that's often easier, because if you can engineer it so that one of the limits of integration is 0, that integral is always easier to evaluate than it is if you're trying to substitute -2 and 2 in. Okay, so your area, everything's above the x-axis here, so we could do the integral from -2 to 2 of the function, which is x squared plus 1, with respect to x. Or that's the same as 2 times the integral from 0 to 2 of x squared plus 1, because of the symmetry. So if you can make use of the symmetry of a function, that's often a helpful thing to do. Okay, so we're going to have 2 times, our antiderivative is going to be x cubed on 3 plus x from 0 to 2. So it's 2 times, we sub in 0, and subbing in 2 first, we get 8 on 3 plus 2, and then take away, subbing in 0, we get 0. Okay, so it's actually 2 times 8/3 plus 2. Now 2 is 6/3. Okay, 8/3 plus 6/3 is, 14/3. And we've got 2 times 14/3, so that is 28/3 square units. Obviously you can write that if you want as, what would that be, 9 1/3, but 28 on 3, improper fraction in simplest form is perfectly fine. Okay, example 4. Calculate the area of the region bounded by x squared minus x, x equals 0, x equals 3, and the x-axis. Okay, so x squared minus x, if we factor out an x, it is x times x minus 1. So it's a parabola with x-intercepts at 0 and 1. Okay. Try and draw that a bit smaller, sorry. Okay, for a particular reason. So that's y equals x squared minus x. This is 1. This is 0, obviously. So we want the area of the region bounded by that curve, x equals 0. So bounded by the curve, by x equals 0, by x equals 3, which is going to be somewhere over here, and the x-axis. Okay, so the regions bounded by those lines are this bit in here and this bit over here. Okay, so if we just calculated the integral from 0 to 3, this bit of negative area between 0 and 1 would cancel out a bit of the positive area between 1 and 3, and we would actually get something that's just equal to, this, if we just did the straight integral from 0 to 3. So we need to split it into 2 separate integrals. Okay, so our area, I'm just going to move that over. Okay, so our area is going to be the negative integral from 0 to 1, but I prefer to write that as the integral from 1 to 0 of our function, which is x squared minus x dx, plus the positive integral from 1 to 3, because that region's above the x-axis of the same function. Alright, and so then we need to evaluate that. So antiderivative of x squared minus x is x cubed on 3 minus x squared on 2. We're doing that from 0 to 1, plus same antiderivative from 1 to 3. Sorry, we're not doing that from 0 to 1, we're doing that from 1 to 0 because it's the negative integral. Now, you're going to have lots of fractions, lots of substitutions here. Again, don't skip too many steps in your head, you'll make mistakes, you'll lose a negative somewhere, or whatever it might be. So write out the steps and then focus on simplifying it. Okay, so here we're going to sub in 0, which will be 0 minus 0. Then we're going to take away, I'm going to sub in 1, and that will be 1/3 minus 1/2. And then we want to add, I'm going to sub in 3, which will be 27 on 3, which is 9, minus 9 on 2. Take away, subbing in 1 is 1/3 minus 1/2. Okay, so this is obviously 0. Take away. Now 1/3 minus 1/2, we need a common denominator there. That's sixths. So 1/3 is 2/6, and 1/2 is 3/6. So it's 2/6 minus 3/6, which is negative 1/6. Plus 9 minus 9 on 2. 9 is 18 on 2. Take away 9 on 2 is 9 on 2. The other way to think about it is you've got something minus half of that something. So you've still got half of the something left. And then take away, we've already done this subtraction back here, negative 1/6. Okay, so again, 0 minus minus a 6, that's plus 1/6, plus 9 on 2, and also plus 1/6. Okay, so that's 1/6 plus 1/6 is 2/6. So we've got 2/6. 9 on 2, if we write that as a denominator of 6 as well, that's 27 on 6. And so we've got 29 on 6 square units. Again, you could write that as, what would that be? 4 and 5/6, but improper fraction, as long as it's in simplest form, perfectly acceptable. In fact, I would say preferable. Okay, example 5, I think this will be the last one. Sketch the graph of y equals negative x squared plus, minus 2x plus 15 and find the area bounded by the curve and the x-axis. Okay, so it's y equals negative x squared plus 2x minus 15, which is negative, what's that going to be, x plus 5x minus 3. And so it's a sad parabola with x-intercepts at negative 5 and positive 3. Okay, so it looks something like that. Negative 5, sorry. And so we want to find the area bounded by the curve and the x-axis. Okay, x-axis, curve, and so therefore we're looking at that region in there. It's all above the x-axis, so that's a nice easy thing in terms of the integral. We don't need to split it into two separate integrals. It doesn't matter that it crosses the y-axis. The y-axis is completely irrelevant. The whole region is above the x-axis, and so it's just going to be one integral. The area will be found by integrating from negative 5 to 3. The function, which is negative x squared minus 2x plus 15 with respect to x. Now you could, if you want, use symmetry and think about the fact that the turning point is, what's that going to be? That's 8, so this will be at x equals negative 1. You could integrate from negative 1, not positive 1. You could integrate from negative 1 to 3 and double it, but there's really no need to do that here. Although, you know, negative 5 is not going to be very nice to substitute in, so it might not be a bad strategy. Alright, let's focus on antiderivative first. So negative x cubed on 3 minus 2x squared on 2, so that's just x squared, plus 15 from negative 5 to 3. Okay, so subbing in 3, we're going to get negative 27 on 3, so that's negative 9, minus 3 squared, which is 9, plus 15. Take away, subbing in negative 5. Now, negative 5 all cubed is negative 125, and then we've got the negative out the front, so that will be 125 on 3. Take away, negative 5 all squared is positive 25, and plus 15. Okay, minus 9 is minus 18, plus 15 is going to be negative 3. And then we've got minus 125 on 3, minus 25 plus 15 is negative 10. Alright, so maybe let's just get rid of those brackets at this point rather than try to combine those right now, because it's easy to put the negative 3 together with the 10. So negative 3 minus 125 on 3 plus 10. So negative 3 plus 10 is 7 minus 125 on 3. Sorry, I just paused the video because I realised this was not going to be right. This is going to give a negative value, and I've just realised I didn't do my antiderivative correctly here. Hopefully you've all picked that up and been sort of screaming at the screen. So that should be 15x there. And so therefore, when we subbed in 3, that should have been 15 times 3, which is 45. And here, when we subbed in negative 5 times 15, well, 5 times 15 is 75, so it'd be negative 75. Okay, so let's fix what we've got going on here then. Let's just go from here on. Okay, so negative 9 minus 9 is negative 18, and then we want to add 45, which will be 27, positive 27. Take away, we've still got the 125 on 3, but now we've got minus 25 minus 75, which is minus 100. Okay, so we've got 27 minus 125 on 3 plus 100. So we've got 127 minus 125 on 3. We're going to need a common denominator to put those together, so we need to work out what 3 times 127 is. 3 times 100 is 300, 3 times 20 is 60, 3 times 7 is 21, so it'll be 381 minus 125 over 3. Alright, so let's just think about 380 minus 125 would be 355, 255, but so it'll be 256 over 3 square units. Okay, and so our area is 256 over 3. So work today is from both exercise 21B and 21C. Key thing is to make sure that you draw the graph first and get a clear picture of the region that you're trying to find the area of, and then work out whether you need one integral, whether you need more than one integrals, whether you need to use negative integrals, etc. So you do need to visualize the region that you're calculating before you just launch into your integrals.